So yes, my job is very easy because already this afternoon we saw talks about noise, optimal stopping, and related issues. So I'm going to focus on what's essentially the role that noise plays in adiabatic protocols. And the talk is going to be divided in two parts. In the first one, noise will be perceived as something that is a bit of a hassle, and in the second part, something that is actually a benefit, something you can use. So I guess this is a common perspective. We all know adiabatic dynamics is pretty good. It gives a good control of a system under slow driving. It allows us to suppress excitations, and it also allows us to find the ground state. So why bother about anything else? And the point I'm going to make is, well, I guess perceived by everyone in the audience, is that there is a fundamental breakdown of adiabatic dynamics in any system which has a critical point. And well-known examples, the phase transition between a paramagnet and a ferromagnet. And so this is essentially what's, why anything else? Well, because adiabaticity gets broken. This is typical it was already alluded before in the talk by Emil. So when you have multiple ground states will have the same energy, and you start in a given phase, say you fix an annealing protocol, you reduce the temperature, and you force the system to choose one of the different ground states. And then, of course, if you do this in finite time, what happens is that the system just cannot make a uniform choice, so domains form, and how many domains you get and what does the size of the domain depends on are questions which are fairly natural, and they are answered to some extent by the so-called Kibel-Surek mechanism, which was introduced by the gentlemen over here. So Tom Kibel, who you might have heard, he passed away a couple of weeks ago, and Wojciech Surek, who is at Los Alamos. So the key ingredient for the Kibel-Surek mechanism is the divergence of both the correlation length and the relaxation time at the critical point. So as you approach a phase transition, then it turns out that as a function of the distance to the critical point, both the correlation length and the relaxation time become very large. And in particular, if the relaxation time becomes very large, that means that you cannot stay adiabatic. It doesn't matter how slowly you go. At this, near the critical point, your dynamics will be non-adiabatic. What the Kibel-Surek mechanism does is to assume that you fix the rate at which you approach the critical point. So the distance to the critical point varies in time as some given function with that characteristic time scale, which is the quench time. And you start, say, in a high symmetry phase, and you want to go to a broken symmetry phase. And I plot here the equilibrium instantaneous relaxation time. And the critical point is reached at time equals 0. So I start some time before. I get close to it. The relaxation time becomes very large. I will be non-adiabatic here, in particular, sort of frozen. And then once I cross the transition, I stay adiabatic again. So the Kibel-Surek essentially mechanism just tells you that this time scale in which the equilibrium instantaneous relaxation time matches the time elapsed after crossing the critical point. At this time scale is crucial to determine all the non-adiabatic properties. In particular, it fixes the size of the domains. The size of the domains can just be estimated by the equilibrium value of the correlation length evaluated at this freeze-out time. We also heard about freeze-out times before, a bit different though. So this leads to a universal power law dependence, so the domain size as a function of the rate, or well, actually the quench time at which you cross the transition. And the exponents are universal, so if you know the universality class of your system, then you just plug them and you get a prediction for the size of the domains. Now, you can also use the Kibel-Surek mechanism to estimate the density of excitations, and it's just essentially, I forget here, -1 is just the inverse of the correlation length in one dimension, or of the size of the domains in one dimension, and it will have a power law dependence as a quench, with the quench time, with the quench rate. Things that we know about the Kibble-Surek mechanism is that it's broadly applicable, so pretty much it has been tested in lots of numerical experiments with integrable and non-integrable models, and it has as well this a whole bunch of experiments which have demonstrated aspects of the mechanism. There is no still uniform, I guess, proof that the Kibble-Surek mechanism holds. There are many difficulties to test it in the laboratory. You have to know the critical exponents, the relaxation time, to measure defects reliably, and so on. Still, we also know, this was some recent results, that the Kibble-Surek mechanism holds even when you do not expect it to hold. So we tested some models given by holography, but essentially the point is that they are so strongly coupled that they don't even have quasi-particles, and it was not obvious a priori that the Kibble-Surek mechanism should hold in this regime. And however, a couple of works show that is actually the case. And so for the purpose of quantum annealing, I guess we are more interested in the implications which manifest in this type of laws. So essentially, the residual energy or the density of excitations is going to exhibit a power law dependence on the annealing time, which depends on the dimensionality of the system, the correlation length critical exponent, and the dynamic critical exponent. Now, in the Ising chain, it takes a simpler form. It's just 1 over the square root of the annealing time. And in the presence of this order, it's quite different. It actually becomes a logarithmic dependence, which tells you that if you want to suppress excitations, you need exponentially long annealing times. So ultimately, for the purpose of annealing, I will say that the Kibble-Surek mechanism is bad news because it tells you you have to stick to long annealing times if you want to suppress excitations. One possibility, which I discussed last year at ETH in Zurich in AQC, was the use of shortcuts to adiabaticity, which essentially are fast non-adiabatic processes that suppress excitations. I'm not going to discuss it today. I just want to mention that there is some good progress in the laboratory to realize, yet in very simple systems, these ideas. Counter-diabatic driving is very similar to the first adiabatic iteration that Sergey introduced in the previous talk. And these are just simple demonstrations for sort of Landau-Zener crossings, 2- and 3-level systems, and also for continuous variables. But if you want to go further, well, it becomes difficult. But I want to mention as well that in the other room, Masoud Mohseni just presented some works which appear in the archive today on how to suppress excitations in a disordered system by inhomogeneous driving. In this talk, I want to return I want to put the emphasis on this type of Kibble-Surek scaling and essentially revisit them in the presence of noise. Here, we always assume that the control field is perfect, so we lower the temperature or a magnetic field at a given rate, but there is no fluctuations, no noise. So I want to consider the effect of noise in the controls. So this is work with Anir Banduta, a postdoc in my group, and Armin Ramani, who is in Vancouver. And this work was actually motivated because when I was analyzing previous experiments devoted to test the Kibble-Surek mechanism, we always saw that there are stochastic fluctuations in the noise in the control field. Yeah, so this is an example. This was just one of such experiments that I alluded before to test the Kibble-Surek mechanism, where they use an ion chain, compress it, they form defects, and the question is, well, what was the effect of this noise? In the context of annealing, I will say that this is the standard schedule where, you have, you start with some simple Hamiltonian, you want to go to a different one, which is somewhat more complex. I'm just going to focus on this example, which essentially is the transverse field Ising model in one dimension, but I'm going to modify the standard protocol and include the effect of some stochastic fluctuations along the process. So I want to see what's the effect of this. So instead of just a linear ramp, I'm going to add a stochastic variable, and I do not need to focus on the white noise limit, but let's just assume that for this is the case, that the noise is correlated as a white noise and it has some strength. Well, so this is something which is well known, at least in numerical methods. There is a whole field known as stochastic Hamiltonians, and this is, if you want, the many-body counterpart of it, where you have a Hamiltonian which has a deterministic part, and a stochastic part, so some Gaussian, say, real process, which is coupled to an operator B. In the annealing schedule, it turns out that this B, this stochastic part, includes both one-body and two-body operators, and just for free, essentially it just comes from the fluctuations of the noise in the control field. And you are led to consider this stochastic Schrodinger equation, which in principle you can just solve by running trajectories and stochastic unraveling. Now, I want to introduce an alternative approach which focuses on the mean density matrix, which is the noise average dynamics. So you run lots of trajectories and you construct, these are the stochastic pure vectors that you get by solving the Schrodinger equation. You can take the average over many realizations and you get a density matrix. Well, it's known that the master equation that this effective noise average density matrix obeys looks like, it has a Heisenberg part, and then it has a relatively complicated open system part. Yeah, so there's a dissipative part, if you want. But now, in the white noise case, it's, one can just simplify this. This is just a delta function, and one can do the exact average over the stochastic realizations, and one gets a very simple master equation, which includes the deterministic part of the Hamiltonian and a sort of a pure dephasing term where B, remember, includes both one and two-body operators. So with this, one can just set the numerics and try to characterize the dynamics, how successful is the annealing protocol by looking either at the density of excitations or the residual energy, which is just the energy with respect to the ground state. And what you see is that in the absence of noise, so for very weak noise, you have essentially the Kibel-Surek prediction holds. So the density of excitations decreases with the annealing time. So long annealing times are always good. But in the presence of noise, there's sort of another contribution which kicks in and eventually gives to sort of anti-Kibel-Surek behavior. This, by the way, has been observed in some experiments. No one had an explanation for that, and here is a very simple explanation, which is just the effect of the noise in the controllers. But you see that it pays off to anneal for longer times only until some time before the sort of dissipative part start to govern the dynamics and leads to this anti-Kibel-Surek scaling. So we can actually extract this universal optimal time. So it's essentially, in some sense, related to some of the previous results. And just when should you stop the annealing process? Well, it depends on the strength of the noise. So, but it scales as a power law, which again is universal. This beta is nothing but the Kibel-Surek exponent, and we get a perfect matching with a power law behavior. And funnily enough, the density of excitations can be well approximated by a Kibel-Surek term times an additive term. So essentially, the dissipative part is just providing a heating with a very well-defined rate, which, again, we can match the rate of this R, which is the heating rate, is just essentially proportional to the strength of the noise. Right, so I guess this was the first part of the talk where noise is maybe perceived as something which can limit adiabatic protocols. Now I want to give a twist to the story and say if I am interested in quantum simulation of many-body decoherence, well, let's think of noise as something good that you can use. So this is work actually with my wife, Aurelia Chinou, Jianshu Cao at MIT, and my postdoc, Matthew Beau, and myself. So it should be soon in the archive. And the idea is, well, I just review briefly the theory of open quantum systems. We always consider a system which is embedded in an environment. So the Hilbert space is the tensor product of the two. The Hamiltonian is the sum of the system Hamiltonian and the environment Hamiltonian. And it includes a coupling which generally you can diagonalize and write as the sum of system operators times environment operators. If you just care about the system, then you derive a reduced dynamics, so essentially a master equation. And what is known is, of course, if it's Markovian, it has a universal form, something that we know since the 70s, thanks to Lindblad. Now, what I want to consider here is, well, the case of many-body dissipators, essentially many-body Lindblad operators. So whenever the whenever the system operators are Hermitian, you can think that the environment is actually measuring these observables. You can think of the system operators as observables. And what I have in mind is a case where the system is actually composed of many particles. So there are many constituent particles, say qubits, collatoms, ion traps, ion chains, and so on. And I'm looking, the system will be able not just to act locally on each of the constituent particles, but it's going to have the chance to look either, for instance, two-body non-local observables or k-body observables. So this type of system operators. Now, it's hard to justify generally this type of master equations because if you want to think you think of this system environment Hamiltonian, this is already two-body, so this will be acting on the system, something acting on the environment. And typically, we know that interactions in nature are well described by pairwise interactions. So in order to have a system operator which is two-body or three-body or k-body, then you need higher body interactions, yes. So the idea is, well, why is this important? Well, there are proposals of how to do quantum computation using dissipation and encoding the ground state or in the fixed point of the master equation. Of course, it's just good to develop a many-body theory of open systems, as there is for isolated systems. Essentially, condensed matter to a good extent is based on that. And then you can use particular type of baths for either adiabatic quantum computation, quantum thermodynamics, and so on. I just want to mention that Alireza Sabani and Hartmut Neven in particular are working hard to get a given type of baths. So this is another approach. So how to simulate this type of many-body decoherence? So the idea is to use now the technique of stochastic Hamiltonians. Again, the idea is essentially just rely on the techniques for quantum simulation of isolated process, of unitary Hamiltonians, and then add noise to make the Hamiltonian stochastic and include essentially the Lindblad terms to reconsider, to include them as Hamiltonian terms, which are modulated by some stochastic forces, which, where eta is just a Gaussian process with zero mean and perhaps some correlations. So if you are able to engineer this Hamiltonian, the claim is that you will be able to do many-body quantum simulation of the coherence of many-body dissipators. And the process follows a similar procedure. You consider the stochastic density matrix, which obeys a Heisenberg equation. You average over noise, so you get a density matrix. And then the noise average dynamics obeys this general type of master equation, which resembles the structure of the general master equations. In particular, you can get the Markov limit, the Markovian dynamics for whenever the noise is wide. Now, here it's the sum over all Lindblad operators, which in principle now can be k-body Hamiltonians. Yes. And as just examples, to illustrate the point, just consider one of the typical systems for quantum simulation, analog quantum simulation with collatoms, is the Bose-Hubbard Hamiltonian, where you have a bunch of particles, bosons, jumping around an optical lattice, and they can have on-site interactions. Well, there are well-known techniques to change the on-site interactions in time. And what I'm proposing here is to make them fluctuate according to a Gaussian stochastic process to engineer this type of dissipators, which becomes already non-local, despite the fact that these interactions are local. Another example, which is readily available to technology in quantum simulation, is the EASY model. There are several platforms to engineer it, but one could just add, again, stochastic fluctuations to the spin-spin interactions and get a many-body dissipator, in this case, with two-body terms or even four-body, depending on how you define it, but two-body Lindblad operators. Now, if you are interested in more exotic Hamiltonians, there's ways to engineer k-body Lindbladians, and the idea relies on the scheme for digital quantum simulation of k-body Hamiltonians. So you will have some given Hamiltonian, which is the sum of some k-body operators. We know about Rotter formula, which allow us to express this unitary in terms of unitaries of its term. And now there are ways in the laboratory to implement k-body Hamiltonians. Essentially, a technique which has already been demonstrated is the use of Molmer-Sorensen gates, which is an entangling gate, and allow us to, for instance, if you want to realize a Hamiltonian of this type, then you can just do it using the action of this Molmer-Sorensen gate, then a one-body, one local spin rotation, and then a inverse Molmer-Sorensen gate. So this is well suited for ions, for instance. And by adding just noise to this one-body local rotation, which is actually very easy, you can engineer this type of n-body dissipator. Yes. So in principle, this provides a very versatile technique to engineer master open quantum systems and master equations with Lindblad operators, which need not be one body, but actually can be k-body. Going beyond the Markovian case is actually very easy. Actually, it's probably the easiest part because you don't need to make a white noise in the laboratory, which is kind of difficult. That, for free, gives you non-Markovian effects. So with this, I close with a summary. So I make the point that the Kibel-Surek mechanism dictates long times for annealing, and that, as I discussed before, at least last year, shortcuts to adiabaticity are one way of preventing the Kibel-Surek mechanism running the process in a short time. And here I focus essentially on the role of noise, either as a source of the anti-Kibel-Surek behavior and a limit to adiabatic protocols, and would suggest the existence of a universal optimal annealing time. And then a second part, which is like making use of noise, essentially harness noise as a resource for the quantum simulation of many body decoherence. So with this, I just want to close and thank my group and collaborators around. And thank you as well.
Any questions for Adolfo?
So regarding the Kibel-Surek mechanism, so in many problems that we are interested in the adiabatic quantum computation, typically they are described on expander graphs, things which are, in this kind of systems, when you cross a phase transition, you do not have a diverging correlation length. So do you expect the Kibel-Surek mechanism to occur?
Generally, the answer will be no. However, if there is, at least if there's a modulation of it, like in a weakly first-order phase transition, something which resembles in some sense a second-order phase transition, then similar arguments can be used. You don't have to be in the thermodynamic limit, for instance. You can actually, with very moderate system sizes, you can already see signatures which, or scalings that agree well with the Kibel-Surek mechanism. But you do need that the relaxation time has a bump. Otherwise, you cannot use this idea of the dynamics being split into a sequence of adiabatic, sort of non-adiabatic frozen states, and adiabatic again.
Yeah, just to specify one thing, so you can also have second-order phase transition, like a ferromagnetic, simple ferromagnetic model on the Bethe lattice. This does not have a diverging length, correlation length. Correlation length is...
Maybe the correlation length is sort of secondary. The key ingredient is divergence of the relaxation time.
Okay.
If something funny happens to the relaxation time, then you can make use of this impulse approximation.
Okay, so there is no relation between the exponents of the divergence of the correlation length, because the correlation length does not diverge, but still you have...
Yeah, I mean, I guess that something happens in BKT phase transitions as well, yes? I mean, so the correlation length behaves in a very different way, but at least you know that you have a divergence of the relaxation time, and then you can modify the Kibel-Surek argument to somehow come out with similar predictions.
Thanks.
One last question.
Maybe you said this, but is there some kind of universality result in the last section about can you simulate all kinds of Lindbladians or some very general family of Lindbladians for some noise processes, or stochastic Hamiltonians, I should say? Thanks.
Right, so I haven't pushed it to full universality. Actually, what I have shown is that if you are interested in a Markovian master equation where the Lindblad operators are Hermitian, then that's it. And it's actually very simple. You can go beyond and add color to your noise, and then you will get a family of non-Markovian equations, which also look like pure dephasing, but really there's a non-Markovian term. And in principle, one could go to the full set of Markovian cases. That requires to add both a complex Gaussian stochastic process, so a noise which is complex value, as well as Lindblad operators, which should be included in the Hamiltonian, but they will be non-Hermitian. So perhaps by embedding into a larger Hilbert space, you can do something like this. Yeah? So I'm thinking about it.
Let's thank Adolfo again.
Cool.